Hi, everyone. So this is the second day of the last lesson, which is Into the Unknown, or lesson 5, Into the Unknown. And we're starting with the talk. And so this is on page 78. We started that with the do now, and then we went to the lesson, which is like 2 pages back, or 3. I think it's 2. And so if you can see here, yeah, we just went through all the problems. These are just like what we did last time in the last lesson, right? Just solving for radical equations and then checking them just to make sure that they work. And all the work is here, as you can see. Notice right here in A, it is the only thing that's on the left-hand side is the square root. There's no other things outside of the radical. So we're going to just start off with the square. We're going to square both sides. Okay. And so just an FYI, because I noticed that there were some people who they were like, well, what do you call this thing? So this, in general, this is called a radical, right? But if we're talking specifically about the square root, then it's just, we just call that square root. So this is the square root. And then when we do it to something to the second power, that is called the square. So we're squaring it, right? And then, so then this one right here would be called the cube root, right? Sometimes for me, I need to see it. Like if you like say your name, I'm like, can you spell it out for me? So it helps me to make that connection. And so if it's something like x to the third power, so we call that cube, x cubed or x cubed or x cube, x cubed. No, it is with the D. I'm like, that doesn't make any sense. Yeah, so we cube it. Okay. And then if you have it to the a fourth, this would be a fourth root. So we call this guy a fourth root. And then so on and so forth. We don't have any special names for them. It's a square because actually, like x times x, that makes a square because both sides are the same. And then the 3, it's in 3 dimensions. So if all 3 dimensions are exactly the same, we call it a cube, right? So that's where the x squared, like the square and the cube come from. And then we don't have a 4th dimension, so therefore it's just to the fourth root. Okay, so it's a closely tied in with geometry. Okay, so if you look at this, so it is squared. Yeah, please do this. If you did not do this in class, you only did or you only did it partially. Finish those up, pause, do a thing. All right. So, and then once you get rid of the square root, it should very much look like what we did in algebra 1, right? You just basically solve for x. So add 1 on both sides, then divide by 2. Answer's 25. And then from there, we're just going to do the check. Make sure that you're putting the 25 in for the x of the original equation, right? So this is the original. So that's where we put the 25 right here. Let me just highlight that for you. So this, right, x 25, it's all the same. And so remember, we don't know if it exactly is equal to 7. So that's why we put the question mark. And order of operation reigns supreme here, as always. And we get the square root of 49, which it is 7. So you keep on going down until you get to the exact same number. So 7 equals to 7. If you don't have the exact same number, then something's wrong. One of 2 things. And we'll talk about that when we get to C. And same thing with B. I think the only difference here is, notice here we subtract the 15 first, because if you notice, the plus 15 is not inside the radical. It is outside. So we're going to get rid of that first. So we need to get only the square of the cube root by itself until, and then we're going to cube it, okay, right here at the end. And so that's what we did here. And then just remember on your calculator how to write this down, how to calculate this. I'm going to just kind of make this like a partial. Right, I'll use this keyboard so you can kind of see what I'm pressing. So remember that this is going to be -5. So if you go -5 and then to the third power, you're going to get the wrong answer. You're going to get, well, in this case, you'll get it doesn't matter, right? Because it is an odd one. But do note that I will be looking for, and you do need to have these parentheses inside parentheses for the -5, because we actually mean -5 times -5 times -5. And if we don't have the parentheses, that just means 5 times 5 times 5, with a negative in front. So same answer, different type of math. Okay, so that's how you would do that. And then don't forget you do your check. Yeah, just plug in the negative 125 in there, and then the cube root. So again, if you don't know, and you're like, you should know, well, if negative 5 cubed was negative 125, then the cube root of that should lead me back to my original negative 5, right? But in case, you know, you are on the test and you're like, I don't remember. So we just go to function and you go to miscellaneous right here, and you see this nth root. You're going to put the nth root and you're going to put the 3 as for your index. And then you're going to put in negative. And remember, Desmos does not have a separate negative button. It's just the minus button. So that's negative 125, which is what we said was negative 5, right? So that's how that's going to go. And we do note that it is equal, 0 is equal to 0. And technically, the only things you really need to check for is like where it would possibly be not a solution is for the even numbered roots. So like square roots and fourth roots and sixth roots and et cetera, because those are the ones where like your square root can't be negative, right? It has to do, you just can't have negative square roots. If you could remember back to like domain restrictions and all, like we were like very specific about that, right? So if you notice right here, but cube roots, you can have negatives, but this is still a good check just to see, did I do it right, right? This is how you would check that in general. So any kind of equation that you're trying to solve, you could always check your work by plugging it back in. And if you get something like 5 is equal to 0, then you're like, oh wait, they know there should be equal to each other. So where did I go wrong? And your error might have been here where you're trying to solve it, or even in your check. Maybe it's, you know, I've had it before where I did the math right, x is equal to whatever that was equal to, but then I messed up on the checking part, which was sad days. But at least you have that when you're taking a test. So you should be confident in those because you're doing the check. And then if you take a look at C, again, please note that we're just subtracting 5. We're not combining like terms with 2 and 5 because as was noted in one of the classes, that 2 is under the radical and the 5 is not. So you can't put those together. This is actually not a 2, remember, because it's inside a fourth root. So it's in this guy. So we are going to subtract those guys, subtract 5 on both sides. And now we have the fourth root by itself, you know, with the exception of what's inside, but that's inside the radical, right? So the inverse of a fourth root is to the 4th power. So we do to the 4th power. Note here that we put in parentheses, and this time it will make a difference. So if you look over here in the calculator section and you go, okay, so negative 4 to the 4th power. Nope, just kidding. Not gotta put in the right answer. Gotta delete negative 2 to the 4th power. And notice right here, you get negative 16. And you're like, well, that's what the calculator gave me. That's because that's what you told it to do. You have to put in the parentheses. So notice here, right when I put in the parentheses, what happens? It turns into a positive 16, right? Because those are 4 negatives. That means those 2 negatives cancel out. These 2 negatives cancel each other out. So you end up getting 4 positives. All right. And then, yeah, that would be one thing there. And then once you do that, you get positive 16. You're going to now, again, just like how we've been doing. So solve for x, subtract 2, divide by 2. Then you get the answer of x equal to 7. Before we box it in, because notice I didn't box it in yet, we're going to check it. So we're going to put it back into our original equation, it meaning the 7, the x that we found. And we're going to see, is this a solution? And here we go. So order of operations, add 14 first, and 14 plus 2 is 16. So what is the 4th root of 16? Again, we're going to go to function, and we're going to go to nth root. Oops, probably want to do that in a different line. Or just like that, I guess. So again, this is the nth root. That's going to be 4. And then the inside is going to be 16. And that's going to be, if you want to put in the plus 5, you have to make sure you arrow key out, because if you don't, do you see how it's still under the radical? We don't want this. This is not correct. And as you can see, it's 2.1. No, that's not it. So you need to make sure that you either arrow key out or you tap or you like click it so that's outside. and then you go plus 5, right? And if you notice there, it's 7. And just like how we said here, it is 7. And notice it is not the same. We're like, wait, okay, I'm pretty sure I did all this right. So yeah, we would have no solution. Another way to check that is if you see this highlighted part, some people will notice, well, it's a 4th root and it's equal to a negative number. You can't have that, because remember, 4th roots can't be negative. Same thing with square roots. That's like, you can't have that, because what 2 number, like if you get a square root of a number, you're not going to get a negative number, because it's always 2 numbers. Like the square root of 4, right? It's basically how we do that, 2 times 2, right? So if we're multiplying 2 numbers to get this 4, you're not going to ever get positive, like negative numbers, because those it's going to cancel each other out. So it's always going to be 2 times 2. I guess one would say, what about negative 2? That goes into quadratics. That's the quadratic side. This is just talking about the square root side, which is just positive. I suppose I should have said that instead. Erase that last part. That didn't make sense. All right, so I'm not going to delete that. So remember, the square root of 4 is always going to be positive, because because this is never going to be a negative number. Well, okay, there is that. Well, okay, if you have a negative on the outside, right, outside of the square root, then yes, this would be a negative 2, right, because that's on the outside. It has nothing to do with the square root, right? The square root itself, the square root of 4 is 2. But if we put a negative on the outside, yes, it would be negative 2, but that's not part of the square root. So there's that. Hopefully I didn't confuse you guys completely. Sorry. All right. So again, when we get to something like that, it's no solution. Again, on the test, if you notice right here, you're like, oh, 4th root equal to a negative number. Can't have that. Answer is no solution. So you could do that, but just make sure you write in words like, okay, this is why it's no solution. Okay. But if you want to just show me algebra, you're like, I don't have the words for that, I'll just show you with math. Then you would just continue on, and you would expect that they not equal to each other. And if they end up equaling each other, then you'd be like, wait, something's wrong here. Then you go check your work. Okay, so that's how you kind of think about these things. We're not just mindlessly just doing this, right? We've got to do some critical thinking here. All right, so here we go. Here's D. And again, right here, there's nothing outside of this cube root, so we're just going to cube both sides. All right, and then our cube root cancels out. The 3 to the 3rd power becomes 27. And then we're just going to do math. Okay, it's technically, well, it's algebra, more specifically, I should say. So, and you would get the answer of 26 over 4. I would like it to be always, always, always simplify. But when you check it, you don't have to use the simplified version. I mean, you can, but it's just use the 26 over 4. So that way, you know that the 4 on the outside will cancel out the 4, your denominator, right? And just makes it simple. You can use 13 over 2. And if you don't believe me, try it out. It actually works. Try it out for yourself. That's better than me doing it. And then once you do that, so we get 26. And then we add the 1, and you get 27. So the cube root of 27 is 3. Happy days. Yay, we're done. All right. And that is not the end of our lesson. That was just our do now, which was kind of super long. All right. So here we're on page 76. And this one, I would really read this section right here. It is interesting. If you're into meteorology, like weather stuff, right? I didn't really know about this stuff. So this is, I Googled some pictures, and this was like a pictorial version of the Beaufort Scale. So the Beaufort Scale are these like numbers, and notice, okay, the one got cut off, I'm sorry. So 1, 2, 3, 4, it's a level 2 or level 3 or level 5. You know, you hear like these, like it's a level 10, maybe it's not level, I'm sorry. But that's what these are referring to. They're referring to how fast the winds are blowing. Okay. And right here, this link right here, this kind of talks about like what, it just gives you more information about it if you're curious, right? I just thought I'd let you know. And so if you can see right here, a level 12 is like devastation. Like this is hurricane level, sad days for you. And so hopefully you'll never have to see something at the level 12. Maybe level 6, I think would be fun, right? But definitely not at 12. And if you notice right here, there is a formula that converts these miles per hour to these Beaufort numbers, right? So it's going to be V is equal to 1.837 B to the 3/2 power. And so this models the relationship between the wind speeds. Okay, so it always defines them for you. So wind speeds in miles per hour. Okay, and so that's our V. And then the Beaufort numbers, which obviously would be B. Okay, so V and B. You got to be very careful how you do this. So the first thing is we're going to solve for B. Why? Just so that we could practice, like, this is like inverting equations, right? Even inverting functions like we did in lesson 2. Graphically, we did in lesson 1. And so this is just practicing that. So we're like, okay, how do we get B by itself? Okay, the first thing you would do is get rid of the multiply. Remember, it's reverse order of operations. We're undoing our order of operations, right? So that's what we're going to divide by 1.837. And then once we get that, we get this pink part right here. Now the question is, how in the world do we get rid of this 3/2? Like, it's an exponent. Like, what do you do? Well, remember, you have to think, how do you multiply it? Remember, if it's a power to a power, that's multiplying, right? You're multiplying the powers. And we want it to be a 1, right? And some people had suggested, well, you can just multiply by the reciprocal, which means just flip the radical, and flip the fraction, and it'll be 2/3. So if we do the everything to the 2/3 power, right? That's going to cancel that out. So all we're going to have left is just 1 on this side. And on the left-hand side, we're going to have V over 1.837 to the 2/3 power. So this is what we would end up with. You could have done this, just change these to radicals, as that's what somebody did in class. Well, in a class, I should say. So notice right here. So this one, remember, the bottom number is the root. Think about trees. And where are trees? Well, where are trees? Outside, right? Where are the roots of trees? Under the ground, right? And where in the fraction, where would be under the ground? Underneath the fraction bar, right? Lies the roots. And so that's going to be our 2. So that's going to be, so notice we didn't write an index number of 2 just because it's assumed that it's a 2, right? And then so that's going to be square root and then b to the 3rd power. So the power is up here, because they think of power like the sun. And where's the sun? In the sky. So that's up here. All right. So it's going to be b to the 3rd. And so then from here, what we can do is it'll take a few more steps. So notice, to get rid of the square root, we got to square it. Okay, these are things that we've just been doing, right? We've been doing these things. And so we're going to square both sides. So there's this pink right here where it's squared. And so now notice the square root has disappeared now. And now how do we get rid of this cube? You got to cube root it, right? And so you do that and you end up with this right here. So as b is equal to the cube root of v over 1.837 squared. That's what that would be. And if you notice, that's exactly what we have here. Notice this root is 3. So that's why the 3 is on the bottom. And we have an exponent of 2. And we have a 2 right there on top. Took us a couple more steps. So either way you want to do it, whichever way makes more sense to you, do it that way. All right. But you should be able to recognize that those are the same things. All right. So then from here, I'm going to stick with the ones with the exponents. And all we need to do now is determine the Beaufort number for a wind speed of 20 miles per hour. And if we look up here on the chart, because this was technically not in the book. So, if we look at this chart, the 20 miles per hour is right here. So we're expecting, a number that's about 5, right? And so we're literally putting in the 20 miles per hour. That's our V. I'm thinking like velocity. Maybe that's why it's V. So that's gonna be 20 right here, divided by 1.837, and then do that to the 2/3 power. And so you would do this on Desmos or whatever calculator you have. And you're gonna be like, okay, don't forget your parentheses. And we're gonna go 20 divided by 1.837. And don't put the end parentheses here, because then it's gonna put that on the bottom and make things more complicated. We don't want that. And then we're going to just click outside. You can, it'll do the parentheses automatically for you, but I just like to push it. And then we're going to go to the, so it's the A to the B, 3/2. And I just check here just to make sure that it stays as a fraction. And if you do not have one of these calculators that just do the fraction thing for you, you may need to put parentheses around them. Just saying, or else it'll just divide the whole thing by 2, and it's just bad. All right, so that is what we want. Or if you want to put 1.5, that totally works, because 3/2 is the same thing as 1.5. Either way is okay. Here's my proof to you. and some of you guys may not have known that you can do that. You're like, oh, you can just do that. I'm like, yeah, you can do that. Like most people will say, oh, that makes sense. I should probably put that as a power 1.5. There we go. See, same answer. All right. So, and did you guys notice what I noticed? Darn it. Okay. So if you saw what I did, and you're like, that's not 5. I'm like, and I looked at it, I'm like, that's not 5. So I was like, oh yeah, it's supposed to be 2/3, not 3/2. So maybe you knew that, or maybe I did that on purpose. Who knows? So let me just change these numbers right here really quick. And there we go. Oh, that's much better, which would be, so that would be like 0.666. Oh, I forgot. To the power of 0.666. 7. We're rounding it at that point. So do you see how it's pretty much the same thing? It's a little bit different at the end because, this is not, I rounded it instead of, continuing this. Remember, 2/3 goes on forever and ever. So, but that's close enough. We don't need it to be more exact than that. So 4.912, okay, right here. And so, which is about 5, which is what we were expecting, right? So excellent. That's what we're looking for. Are those wind speeds okay? Yeah, this looks okay. It looks like just a windy day, but nothing too terrible. Excellent. And so the next problem is the body surface area. So this is actually to help, as it says, to determine dosages, like for medication. So always like if you have like a younger brother or sister, maybe, when you were young, you remember they would ask you about what's your weight? They probably wouldn't ask you. They would probably ask your mom or somebody, right? Whoever took you to the hospital, what's the weight and what's the height, right? And so they need these 2 things to figure out, what the dosage is, or maybe they don't have to ask you because they already have it in their charts, right? And so this is how they would tell, and they would look at this chart right here, right? The body surface area chart, or if they, they have it in their brain, they could just put this in the calculator and you could figure out what the BSA is. Okay, and then that would determine the dosage, like, because they don't want to give you too much and they don't want to like underdose you, so it's like not effective. So they need those things. So and another thing that I pointed out, I looked this up on Google. You could probably look up BSA and see this picture too. So I noticed, I'm like, wait a minute, this is not the same as that. Doesn't it mean the book is wrong? And let's see here. So we know that the weight, so W means weight in kilograms, which is what they have here. So that's good. It's in, this one is last and this one is first, but that's fine because it's just multiplication. They can switch, right? And we look at the height, which is in centimeters, and here it also is in centimeters. So that's also good. But here, this is 60 and that's 3,600. That's a really big difference. Is what's going on. Some people noticed, like, oh, the 3,600 is actually under the square root, whereas the 60 is not in the square root, right? So if we do the square root of 3,600, maybe some guys already know already, but here it is, square root of 3,600, 60. So yay. So yeah, we are good. Oh, we don't need that. I didn't. Okay, so so that is the same thing, just written a little bit different. This is a little bit more in the book. It's a little more simplified. And we are going to solve for H. So first step is, well, okay, and figure out where H is. And I'm like, oh, H is here. And then okay, got to get rid of everything else. So we're like, okay, we got to get rid of the 60 first. So we're going to multiply both sides by 60. And then we're going to get rid of the square root. So we got to square both sides. And when you square both sides, you must remember to square the 60 as well, right? So the 60 squared is 3,600, which, remember we talked about that already. And then the square root disappears because it got, canceled out. So now we're just going to divide both sides by W. So we get H is equal to 3,600 B squared over W. That's it. All right. Again, good practice. The more you try it out, it'll make more sense to you in your brain because your brain is trying to figure out a thing. So again, determine the height of the patient who weighs 90 kilograms. If you go 90 times 2.2, it's about, I think, 198. I don't remember. I did it at one point. I don't remember. Pounds. And then has a BSA of 2.1. We're kind of trying to backtrack here, right? Like, wait, what was their height, right? And so we're going to put the 2.1 in for B and the 90 in for the weight. And you put that into your calculator and you should have gotten 176.4. I think that's what people had said. And so we're going to go actually over to the table and we're going to see if this is true. Okay, so if you look right here, there's this huge chart. This is not even all of it. This is like half the chart, right? This is why probably it would be easier for doctors to just put the calculations in, right? If they remember that, just be way easier. So notice the top one is weight and the one on the left is height. Again, in centimeters, like they said. And so remember the weight was 90 kilograms. So I'm going to use some annotations here. Let's try and figure this out. So we're going to look at 90. And all these numbers in the inside, that's the BSA. Okay. Normally they would have the weight and they would have the height and they could just be like, oh, the BSA is this. But in this case, we're kind of going backwards. So we're going to kind of do some detective work here. So I'm going to kind of scroll down. So that blue line is to kind of help us kind of see which column we're looking at, because there's a lot of things going on there and you may have to look very closely. So we're looking at right here, 2.1. So 2.1 is in two different places. It is, let me see if I could find a different color here. So 2.1 is right here, right? So we're going to go across. So it's going to be in between those two guys. I'm going to slowly go across. And if you notice, it's going to be somewhere in 176, 177, somewhere around there. And so we'll take a look at our answer. Yeah, 176.4, exactly, just like what we said. So that would be, this is the chart, and this is how they're getting all these numbers inside there, right? Can you imagine having to do all the calculations by hand, like all of these and fit them in? Good thing we have a spreadsheet for that. Spreadsheets can do all that for us, thankfully. Happy days. All right, so we're gonna go on to, so that is BSA. And the third one, which we a lot of us went over in class, is the pendulum. We're bringing it back. And so Big Ben is the nickname of the bell in a well-known clock tower in London, England. And I'm sure, I don't know, have you heard of Big Ben? It's very famous. And apparently it's in London. And so if you notice right here, so the clock is driven by a 660-pound pendulum in the clock tower that continually swings back and forth, right? And so this was built like over 100 years ago. It's very old. And when I was reading, it like took about 16 years to build the thing. Like that's a lot. But my question is, like, so the pendulum is like right here. It's like it swings back and forth. I don't know if it has a ball or what, but well, it probably will. But okay, obviously it's not going to go outside of the building because we want to keep the building safe and structurally sound, right? But it's going to go back and forth like this, right? And it doesn't go all the way. I thought it might go all the way down, but it doesn't. It's just like, you know, like this. I don't know exactly how, well, actually we're going to find out how long it is, but I could not find any pictures of it. That's all I'm going to say. And but this clock, this pendulum is 660 pounds. That's probably why it took 16 years to build the thing, because how are you going to bring that up? 660 pounds, that's not easy. I don't even know, especially back then. Like you didn't have like the mechanics you do now, right? And if you notice right here, ooh, and I did show you guys this. So this is the top of the pendulum. This is as much as I could find about the pendulum. So this is the, you know, like the top of the pendulum, you know how it swings. So it's the top right here, right? How far up? It's pretty far up, I think. And so they have these like coins on there, and those coins apparently are there for a reason. It's not just to be there, just to be there. It actually, they like literally like take off a penny so that, and when you take it off, what happens to the weight? It gets lighter, barely lighter, but still lighter. So that actually changes the swing by a fraction of an amount, right? So they're trying to be precise here. Apparently the person who's in charge of all this is called the Master Clock Keeper. That's a cool title, right? That's a kind of cool title. So they can determine whether it's going too fast or too slow. They'll like add a penny or they'll take off a penny. And you know literally how much that changes? Like 0.4 seconds per year. Like that's all you're losing, right? Or adding, whichever way, right? And so it's not even a lot, but so that they're there for a reason, because if you take all those off, it's going to be the wrong time. And then where will London be, right? It'll be sad days. So we're looking for this length right there, this pendulum length. And we're going to go back to our originally scheduled equation here. Let me go over just a little bit. And so here is, okay, so it says the relationship between the length of the pendulum, L, in feet, and the time it takes for a pendulum to swing back and forth. That's one period, right? So, and that's going to be T. Maybe T for time, T for, I don't know. So anyways, so one swing, so the T is equal to the 2 pi. So T is equal to 2 pi, and then the square root of L over 32. Now, if you think about this, right, this is like, because if you notice right here, this is a, what is it called? That is the radius, right? And if you remember, and if it's swinging, the radius does not change. Obviously, that's why it's called the radius, right? Then we're actually dealing with a circle, right? If we were to go all the way around, it would be a circle, right? And so this is just part of that circle, part of the circumference, right? So that's why the pi's are involved in here, right? Because we're actually talking about a circle, as there's some relationship to that, right? So let's take a look here. Oh, and I guess my question is, then why would they have to take off the pennies and put on pennies? Because it should always be constant, don't you think? Friction, people in physics, you should know. All right, so here, let's go. Let's try this out. Just things to think about. Prove me wrong. Okay, so T, so how do we get rid of this 2 pi? Because that's outside the square root, right? So one thing we can do is just divide by 2 pi. And so you guys may be like, well, that's a fraction and a fraction. We can't do that. We can totally do that. And it doesn't really matter, because if you notice on the left, the T pi's, the 2 pi's are going to cancel out anyways. So all we'll have left is the L over 32. So it worked out. And then we're going to look at this right here. How do we get rid of the square root? The square both sides. Let's just get in the habit of putting parentheses on them. And that'll keep us from getting the wrong answers. And so we got T, oh, yeah, let's go. T squared, we're just going to write it over here. So T squared over 4 pi squared. If you want to leave it like that, you can. Either way is okay. I think in class I kind of left it like that, and that's okay. And then we're going to just divide it. So how do we get rid of that? Divide by 32. We're going to just multiply by 32. Multiply by 32. And then what do we have left? We have L is equal to 32t squared over 32t squared 4 pi squared. So if you notice, some of you guys may sound like we're like 32 divided by 4. We know that. That's 8. So let's simplify more. So L is equal to 8t squared over pi squared. That's it. And so so it says if the period is 4 seconds. Okay, so 4 seconds, that's talking about the T right here. So L is equal to 8 times 4 squared over pi squared. Let's just, okay, we're gonna have to use some decimals here. This is a lot. All right, let's take a look here. So we're gonna go 8 times 4 squared, just like that. And then we're gonna divide that by, ooh, let's do, technically won't be any different, but we'll put parentheses around that just to, so that looks the same. And so that's going to be over pi squared. So here we have the pi button. We're going to square it. There we go. And that's going to be about 12.96911. For those guys who did this in class and we didn't simplify it this way, see how it's the same number? So it's about 13 feet. Yeah, that's only 13 feet. I would have thought it would be longer. It's a little bit disappointing, but that's okay. 13 feet is still good. So now I told you guys in class that I would be doing this problem. So maybe you fast forward to this ending because you were curious, right? I would highly recommend that you just try this yourself. And so, and then maybe press play to see. Okay, so we have a pilot flying high above the earth. She has clear vision to the horizontal, to the horizon ahead. So Yeah, forget the satellite. We're not talking about this. Is a different problem. This is all I could find. I'm like, I wish I could draw this, but that's not my specialty here. So that's okay. So here's the height. That's, because perpendicular to the ground. And the horizon is always, where you don't see any more land, right? This is how we know that the earth is round, right? See, it curves, right? So you can't see like over here, right? Because it's beyond its scope, right? It's past the horizon, right? It's beyond what you can see, right? So yeah, so that point right there is where the horizon is, or what we refer to as the horizon. So if you notice right here, it like makes this like perfect right triangle like this. Okay, now granted, we do know that the earth is not completely circular. It's a little bit, but it's close enough. Okay, and we're dealing with numbers that are big enough that it's okay. All right, so we'll do this. This is a good estimate, let's say. Okay, and so here it says consider the diagram. Oh, and if you notice right here, they do it the other way, but it's still the same thing. I like this one just because it blows it up a little bit bigger. It's a little bit easier to see where the H is and all that other stuff. Right? So let me just title these. So this is their H right here, because that's the horizon. That makes sense. And instead of H, we're going to put in P, because they put in P. Oh, P because it's plane's height. I like that. P represents the plane's height, and R represents the Earth's radius in miles. Okay, so Earth's radius, remember this is the core. Well, we know nobody's ever been there before, but we think it's a core. Well, in the center, right? And then this is going outside. So, there's like all the different, like the magma level and the mantle. I don't remember, right? You guys know more than I do about that. And so here is the surface of the earth right there, right? So from the center to the edge, that's the radius. And we're saying that they're the same. Again, we're assuming that this is completely spherical. Oh my dear. I'm sorry. So let's take a look here. So for letter A, it says derive an equation to show the relationship between the three sides of the triangle, then solve the equation for the distance from the pilot to the horizon, which is the H. So we want H equals at the end, right? So let's take a look. So remember, this is a right triangle and we have all the lengths. Think about it, geometry. What is the one thing that everybody remembers in geometry? The one formula. A squared plus B squared equals C squared, right? So here, remember our C squared is going to be, I'm going to write this in. So this part right here, oh, you can't really see that color very well, huh? I will do this in orange. Maybe orange will be better, slightly better. Oh, look, it looks like my highlighter color is changing, but it's not. It's what's behind it, right? So that is going to be our H, or our C, right? That's our C. Let me erase all these other things because that gets confusing. And then we have this one right here. And honestly, it doesn't matter which one's A and which one's B. So this is my A and this is my B. And we're going to use these. This is just reference. So we're going to use these, the letters that were given to us. So here we go. So we got A squared plus B squared equals C squared. Now, A squared is the same thing as our H. So it's H squared plus B squared, which we've defined as R. So that's going to be our R squared. And notice here, I put, this is uppercase R, but I'm going to use the lowercase r because that's standard practice. And that's, they labeled them lowercase here. So I'm going to stick with that, is equal to, and now C squared is R, not just R, but plus this little bit right here, right? So it's actually R plus P squared. So far, so good. So now it says we want to solve this for H. So we're kind of there. We just need to get rid of this R squared and then the square root. So how do we get rid of the R squared? Oop, not use that color, apparently. Let me just make this a smaller color. So we're going to subtract R squared on both sides. You might be like, oh, those two? No, not at all, because they're not the same thing. This R is attached to the P because they have parentheses around them. So yeah, no can do. So we're going to have left H squared is equal to R plus P squared minus R squared. So R's are good. How do you get rid of the square root? Well, we have to square root both sides. And as in geometry, we are, so let me just write this down first. This is the square root of R plus P squared minus R squared. Now we are going to ignore the plus or minus in this case because we're talking about an actual like thing, right? That we cannot have negative distances. So therefore, we're going to ignore the negative number because we don't need it. It's what we call extraneous information, right? It's this extraneous solution because it's irrelevant here. We're never going to have negative distances, right? H will never be negative, right? So we don't, that's why in geometry, when you were just solving for it, you never really had to worry about it. And probably your geometry teacher didn't tell you to worry about it because we're talking about like actual things that don't have negative distances. So therefore, we're not going to do the plus or minus in case you were wondering. So now that's our equation. So now use your equation from part A, which we have right here, to calculate the plane's altitude. If the height, altitude meaning the height, right? If the distance from the pilot to the horizon is 225 miles. So this is 225, we're saying. And we can look up that the Earth's radius is about 3590 or 3559 100 miles. Okay, or 3959 miles. All right, so we're going to go H is equal to, and we're literally just plugging them in. What is my R? My R is 3959. So it's going to be 3959 plus P, so plus O. Did I do something wrong? Solve for H. Oh, this is just different. The horizon. Okay, we don't know what P is. Okay, I was gonna say, I'm like, wait a minute, we don't know what P is. Then why'd they tell us to solve for H? This is different. All right. I usually try not to do these ahead of time just so that you can see my thought process. So you can maybe learn from that. I don't know, because this is how like I consider myself to be a math person, right? And you're a math person. This is how we would reason it out, right? Okay, so, and the Earth's radius is, so minus 3959 squared. Did I need the parentheses there? Nah, but you know, some people like them. Okay, so now H. H, remember it says H is the distance from the pilot to the horizon. Okay, so now we're gonna have to erase H because we actually know what that is, which is right here. This is H, 225. They just threw me in for a loop. They might as well, they should have just said solve for P. Oh well, that is not my decision. So here we go, so that's 225. So now, okay, we got this, we can do this, right? No worries. So what we're gonna do is, I'm gonna simplify what I can. Well, I'm gonna just solve for P here. So what I'm gonna do is I'm gonna square both sides. The reason why is because the only thing outside of the square root is nothing. So there's just a square root there. So I'm gonna square both sides. And so I personally do not know what 225 squared is. I know it's gonna end in a 5, but okay, let's try. So 220, let's go with the new one. 225 squared. So that's going to be 50,625. Okay. And I usually try not to put commas in here just because it could be a little, I could maybe mistake it for a period, like a decimal point. So I'm just going to leave this like that. And I'm going to figure out what this is right here. Looks like it's going to be a big number. So 3959 squared. Ooh, you ready for this? 15,673,681. 15,673,681. Did I do that right? 673. Yep, Purdue's. Okay, good. All right, so then from here, now these are big numbers, but don't let that freak you out. It's fine. We're okay. We're not dying yet. So remember, just like pretend these are smaller numbers, right? This is 1, this is 3, and this is 5, right? So how would you get rid of the 1? You just add it, right? Because it's subtracting. So we're just going to add this big number. So 1, 5, 6, 7, 3, 6, 8, 1 over to the other side. So plus 1, 5, 6, 7, 3, 6, 8, 1. And then what do we get? Okay, I'm going to need a little bit of help here. So I'm just going to add to this and go plus 50625. There we go. And we get 15,724,306. 724,306. Just to make sure. 724,306. Yep, there we go. And we got 3959 plus P, and then everything is squared like that. Not terrible. It's slowly getting a little bit smaller, right? This first one was like, what in the world? And now, you know, we're figuring it out. So how do we get rid of the square? Got to square root it, right? We're going to just square root the side, square root both sides. And again, we're not going to deal with the negative parts. We're not, so since we square rooted both sides, we're not putting the plus or minus because we don't care about the negative ones because the negative answer is not going to be an answer. So, okay. So we're going to take this number. Ooh, I wonder if I could just take this number. Can I copy this number? Okay, never mind. I'm just going to, so we're going to do the square root of, this is where I wish I had an actual calculator. I could have just done square root of the answer, but oh well. 4306. And we get about 3965.39. So 3965.39. I believe it's 0.39. Yep, it is. And we get is equal to 3959 plus P. Are you ready? So now we're just going, we're almost there. Don't give up on me. You got this. Now we're just going to subtract 3959 from both sides. And so we are almost there. We're just going to subtract. So it's going to be 3965.39 minus 3959. Remember the radius, we're taking that out. And oh, delete. And that's going to give us 6.39. So 6.39, and that's going to be what the plane's height is. Now that better not be in feet because that means that the plane is landing. And if you look right over here, if we look at the P, it says P represents the plane's height above the earth or altitude in miles. So PU. So this makes sense. So they're about 6 miles above or close to 6.5 miles above the earth. They're really, 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 really high up. Okay. So yeah, so they're 6.39 miles above Earth's surface, just to be, you know, clear. Above the Earth's core. They're inside the core. All right, so that's pretty much it. All right, I will see you guys later. Hope this was helpful. Bye.